So today we'll start with the last topic of this controllability week. This is called the stabilizability. So in this week we will study about the stabilizable system. So one important thing with which we concluded in the last lecture of controllability, that we did some decomposition of the overall system into controllable and uncontrollable modes. So now we want to know that once we have obtained the decomposition and the rank of the controllability matrix is, let's say, n bar less than n, then we would like to know that whatever the uncontrollable states are, whether they are at least stabilizable. Stabilizable is a weaker condition than controllability, because we know that if the system is controllable, or if the rank is full rank, then it means all the states can be taken from uh, xt0 to xt1. Okay, so first we'll introduce the definition of the stabilizable systems. Then we will see three different tests for stabilizability, similar to what we had seen for the controllability: the eigenvector, the PBH test, and the Lyapunov test. So this figure demonstrate the decomposition, the block diagram decomposition with which we had concluded. So we see that U only has an impact on the controllable states, and through any path U does not have any impact on the uncontrollable states. So you cannot influence the XU states. Okay. So earlier we saw that any LTI system is algebraically equivalent to a system in the following standard form for uncontrollable systems. So we are representing the continuous time and the discrete time by a derivative and by the advancement in time respectively. So this is the upper right hand side triangular matrix in which we have decomposed, and similarly the B matrix by introducing a non-singular matrix. So if you want to recall the definition of algebraically equivalents, it was discussed in detail in the first week when we discussed about the state space solution and realization. So the definition of stabilizable system says that the pair AB is stabilizable whenever it is algebraically equivalent to a system in the standard form for uncontrollable systems, that is this one, with n is equal to n bar, that is AU is non-existent, or with AU a stability matrix. So first of all, try to visualize the implication of this definition in the sense that once we have obtained this canonical form or the standard form of the uncontrollable mode, the dimension of this AC matrix is n bar cross n bar, and this XC is the controllable states. Now XU is the uncontrollable states. So if I write the equation for the uncontrollable mode, it would be XU dot is equal to AU XU, and this is nothing but your homogeneous system, which is not at all influenced by any input. Now this AC or the state XC is controllable, so it does not matter whether the eigenvalues of the AC matrix are on the left hand side or on the right hand side. But whenever the eigenvalues of this AU matrix lie on the left hand side, then we say that the systems are stabilizable. Okay, if the eigenvalues of AU are on the right hand side, then you cannot, or the system is completely uncontrollable. Okay, because it does not even satisfy the weaker condition of stabilizability. Okay. So let's see. So this is the homogeneous system in terms of the uncontrollable states, where AU is a stability matrix. So we know that XU converges to 0 exponentially fast, and we can write the equation only for the controllable states, where this D is nothing but your A12 XU. If you have any difficulty to visualize this one, so if I write only the first equation, that is for the controllable state, so I would have XC dot is equal to AC XC A1 to XU. So this part I have written as another signal D, and similarly I would have the similar representation of XU in terms of another signal called N. So both are in fact time dependent. So these two signals can be viewed as disturbance and noise stem respectively that converges to zero exponentially fast. Okay. So in fact you can represent this system in the form of, let's say, XC dot is equal to AC XC comma D. And here you can say that this is some input U bar. Okay. So either you use this representation or this representation. So this is U bar. Okay. And this is the block diagram representation only of the controllable state, where this D is your uncontrollable state and N again the uncontrollable state with the output matrix. Okay. So there are, if we want to test for the stabilizability, or let's say if the controllability test has been failed and we want to check for the weaker condition of stabilizability. So there are two steps. First we do the decomposition, and then we see that whether the uncontrollable states are stable or not. Okay, so there are two steps to go to verify whether my system is at least stabilizable. So if we do not want to do these two steps, we are now interested in computing directly whether the system is stabilizable or not. Okay, so these three tests which we spoke about in the outline, so those tests ensures that without even decomposition we can carry forward those tests for the stabilizability. So let's say we want to investigate the stabilizability of the LTI systems, either it could be continuous or discrete, from the definition which does not require the computation of the uh, decomposition matrices. Okay, so first one is the eigenvector test. So this result says that the continuous time system or the pair AB of the LTI system is stabilizable if and only if every eigenvector of A transpose corresponding to an eigenvalue with a positive or zero real part is not in the kernel of B transpose. So if you recall the definition of the controllability or the eigenvector test for controllability, it was without this uh, blue colored words. So it was that the eigenvector, that every eigenvector of A transpose is not in the kernel of B transpose, irrespective of whether the eigenvalue is on the left hand side or the eigenvalue is on the right hand side. But when we are testing for the stabilizability, we need to ensure that the eigenvector corresponding to only unstable eigenvalues is not in the kernel of B transpose. Okay. Similarly, for the discrete time system, the condition of unstable eigenvalues would turn into the eigenvalue with magnitude larger or equal to 1. Okay, which are outside or on the boundary of the unit circle. So first of all, we will recall a couple of things, and these three equations are pretty much clear to you, that the A bar, which was decomposed into this form by using a non-singular matrix T, similarly the B bar, and this transformation matrix between the two vectors x and x bar. So the proof, this is a if and only if proof. So first of all, we'll see this implication that if the pair AB is stabilizable, then it implies that every unstable eigenvector of A transpose is not in the kernel of B transpose, or does not belong to the kernel of B transpose. Okay. So we'll prove this by contradiction. that is to say that there exists an unstable eigenvector of A transpose which is in the kernel of B transpose, implies that the pair AB is not stabilizable. Okay, so assume that there exists an unstable eigenvalue eigenvector pair lambda x for which these two equations would satisfy that A transpose x is equal to lambda x, meaning to say that x is that eigenvector corresponding to an unstable eigenvalue. That's why we are calling it an unstable eigenvalue eigenvector pair lambda x. Okay, and since this eigenvector is in the kernel of B transpose, we would also have B transpose x is equal to 0, which is equivalent to saying that I can replace this A matrix and B matrix by its decomposed counterparts, which is your T A bar T transpose, T inverse, and here B would change to T into B bar. Okay, again expanding this T A bar T inverse, I would have this decomposed form with the respective transposes. T transpose x is equal to lambda times T transpose x. Okay. Now note that here that I can write. So first of all see this one. We have this T B bar transpose, which I can write as B bar transpose and T transpose. Okay, now if you recall that we have represented T as U as this matrix. Okay, where we know that B bar is your BC transpose and 0. So I can write this part as equal to this part, which is again equal to 0. So and T transpose x is nothing but your x bar, which is given by here. X bar is the decomposed form of xc and xu. Okay. Similarly, T transpose x would become x bar. The rest matrices would remain the same. Similarly, it would happen here. Okay, where we know that this x bar is equal to T transpose x and is not equal to 0. Clear up to this point? So moving forward, since we know that the pair AC-BC is controllable already, meaning to say that there is an eigenvector xc which satisfy these two equations, and since xc should be 0 only because it cannot satisfy both these equations. If it for this eigenvalue, if we have this xc, BC transpose xc should not be equal to 0, right? And if there is some xc satisfying these equation, it must be 0. Okay, so xc we have 0. Now note that here that in this equation we have xc and xu. Xc and xu is not equal to 0, right? And we already know that xc is equal to 0. It means that xu should definitely be not equal to 0, right? Therefore we have consequently xu is not equal to 0 because the complete vector itself is not equal to 0. Okay, since otherwise this would violate the eigenvector test for the controllability, right? So this says that this means that the lambda must be an eigenvalue of AU because A transpose U xu is equal to lambda xu, which contradicts the stabilizability of the system because lambda is unstable, right? So this completes the proof of this part. The second part would be the other way implication, that is to say that every unstable eigenvector of A transpose, if it is in the kernel of B transpose, then it implies that the pair AB is stabilizable. Again we will follow the negation approach, that suppose now that the system is not stabilizable, so we want to prove that there is an unstable eigenvector of A transpose which belongs to the kernel of B transpose. Okay, so suppose that the system AB is not stabilizable. So therefore what we had seen in the last part of the result, that AU transpose has an unstable eigenvalue eigenvector pair which satisfy this one, being xu not equal to 0. Okay. Now here I have explicitly written that xe is already equal to 0. And xu is not equal to 0, that's why we are not writing xe and we are writing 0 in place of xe. This a bar transpose into x bar having xe is equal to 0 is equal to the transform matrix and the transformed state, okay, which would be nothing but equal to lambda times u xu. Okay. Similarly, if I expand this thing, it would become b bar transpose into this state vector in fact become equal to 0, because we have xe equal to 0. But we also know that x bar is not equal to 0. So we have thus far found an unstable eigenvector of A bar transpose in the kernel of B bar transpose. So this pair A bar B bar cannot be stabilizable. Now since both these pairs AB and A bar B bar are algebraically equivalent, so the so when we say that A bar B bar cannot be stabilizable, it implies that A bar B bar, oh sorry, AB, the pair AB is also not stabilizable. But we can see to conclude that the original pair AB is also not stabilizable, we use the equivalence shown in part 1 to conclude that. So that equivalence is basically this equivalence. Right? And in fact it is straightforward also by taking the definition of algebraically equivalent, that proving that A bar B bar cannot be stabilizable in fact implies that the original pair AB is also not or cannot be stabilizable. Okay.